All right. So thanks. Today our speaker is Viswambhara Makam, who is at right now at Institute for Advanced Study in Princeton, and he's supposed to move to University of Melbourne very as soon as one can during this pandemic. So that he has a position, research fellow position at University of Melbourne, a very prestigious one, and I would like to thank him for accepting my invitation. And he's going to tell us about maximum likelihood estimation and invariant theory for tensors. So, Vishu, the floor is yours.
Thank you very much for the invitation. It's been 10 years since I last visited ISI Bangalore. That was when I was trying to get into the undergrad program. It feels kind of nice to be back with a different stage of life. Anyway, so today I want to tell you guys about this kind of a very fascinating story that I've been part of in recent months, and it's about this thing called maximum likelihood estimation, which is a concept in statistics, and we are going to relate it to invariant theory, which is one of the subjects I've been studying for a while now. It's my main research interest, and the setting in which we're going to study both of these things is the setting of tensors, which generalize matrices but are often much more complicated. So this is joint work with my advisor Harm Dirksen and Michael Walter, who's at University of Amsterdam. So before I start the talk, let me just say, I really can't see you guys. So if there's something off, please speak out. Okay, so I'm going to start the talk now.
Sure, yeah.
Okay, so I'm going to start with telling you a little bit about invariant theory and how I view invariant theory. Then I'm going to turn towards maximum likelihood estimation, explain the statistics concepts, and then bring it back to invariant theory and then solve whatever problems we were trying to solve. Okay, so invariant theory I think of as a study of symmetries captured by group actions, but this is maybe a little bit too generic in definition, because this could probably be the definition for many subjects that you can think of. So I will be a little bit more specific. I want to say why functions that are invariant by the group action, invariant under the group action. So that's what invariant theory looks for. It looks for quantities that don't change under the group action and uses it to study the group action. Okay. Now it began with in the 19th century with the so-called masters of computation. And some of these names that I've put here, you see in various algebraic subjects, whether it be algebraic combinatorics, whether it be representation theory, whether it be Lie theory, algebraic geometry. You see these names, and because a lot of those subjects have their beginnings in invariant theory. And many of the contributions of these people, it's kind of fundamental, really began because they were interested in things that you would call at that point of time invariant theory. The modern foundations, however, I want to give credit to Hilbert, Noether, and Weil, and maybe a couple more around that time. So right about the turn of the 20th century, these people laid down a bunch of very important results that kind of changed the face of the subject and algebra in general. For example, Hilbert's papers, he was trying to solve something in invariant theory, and incidentally, he proved his lemmas, the Nullstellensatz, and things like that, which is basically the basis of modern algebraic geometry and commutative algebra. Now, what is so good about invariant theory today, which looks very different from invariant theory back in the 19th century, is that today we have, a mix of, so it has many aspects to it. It has a theoretical aspect to it, which of course goes back to the 19th century. It has a computational aspect to it and an algorithmic aspect to it. So the computational aspect of invariant theory sort of grew into prominence about the 1970s when people first started getting computers, and then ideas such as Grosvenor bases and so on came to the forefront. And the algorithmic aspects are even more newer, maybe the past 2 decades or so, where connections to the geometric complexity theory program, which some of you must have heard of at some point of time, which sort of relates it to fundamental problems in computational complexity, such as P versus NP, and so on. So the good part about invariant theory is that you can often switch between these different aspects. And what this allows you to do is it allows you to take strong theoretical results and apply them to places where you actually want concrete answers. And today we're going to see an example of that. And the example of that is going to be a context of statistics. There are, of course, many other examples. My advisor recently put out a paper where he's using invariant theory to come for crater identification on the moon, and I think it's really being used. It's not just a theoretical piece of work. Okay, so now let's move on to statistics. I'm going to start kind of slow. So a statistical model is just a collection of probability distributions, and we're going to just put our underlying space to be d-dimensional real vector space. So a statistical model is just a collection of probability distributions. And often what you have is you've observed some empirical data. So you have a certain data that's been observed. And then you want to figure out from this collection of probability distributions, which was the most likely distribution that this data came from. Okay. And this, of course, you have to interpret it more concretely and more mathematically, and we will do so. But so the kind of technique that we will do is we will try to maximize what's called the likelihood. So for every probability distribution function, you can, so given this particular set of observed data, for any probability distribution function, you'll write down a function called the likelihood. That'll tell you what's the likelihood of observing this particular set of data if you started with this particular probability distribution. And then you try to maximize it over all the probability distributions in your model. Now, the kind of questions that we are going to be interested in is going to be something like, how many samples do you need to be able to identify this most likely distribution? If you had just one sample, maybe it's very hard. But maybe you need 3, maybe you need 7 before you can try and identify this most likely distribution to some degree of accuracy. All right. So that's the kind of questions in statistics that we're trying to look for. So let me now tell you what this likelihood function is, because this is what I'm going to try and maximize. So I will slowly add in technical terms. I mean, they're not really technical. I'll slowly add in hypotheses to get to the situation I finally care about. So the first hypothesis that I'm going to do is the probability distributions I'm going to think that I'm going to study are going to be multivariate Gaussian. So some of you may be familiar with these things, but if you're not, then so here's what a multivariate Gaussian distribution is. You take a matrix which is d by d positive definite and call it the concentration matrix, which I'm going to call psi. Then you give a probability density function, because this is going to be a continuous distribution. And the probability density function is given by the formula determinant of psi over 2 pi, take the square root of that, times e to the minus 1/2 y dagger. So I just put dagger there because it should really just be transpose, because we're over the real numbers. But I put dagger there because you might also consider complex distributions, in which case that would be conjugate transpose. Anyway, so I'm just going to say transpose. So e to the minus 1/2 y transpose psi y. Some of you might have seen this formula with a covariance matrix instead of a concentration matrix, and the two are just related by the covariance matrix would be the inverse of the concentration matrix. I only picked the concentration matrix because it looks simpler. There's no difference. Okay, so that's what multivariate Gaussian distributions are. Now, let's just say you have m samples. Each sample is just going to be a vector inside d-dimensional space. What is the likelihood function? The likelihood function, we just are going to write it down. The likelihood function is just you multiply the probability densities of each of the samples you've observed. Okay, so I just want to point out that this is not really the probability of seeing this, because we're in a continuous distribution. So we can't really write the probability of seeing any particular set of data. But if this were a discrete distribution, then this would really be just the probability of observing y if you started with the distribution psi. But because you're doing the continuous setting, I mean, it's still sort of reflective of the fact that if the likelihood for one data point is higher than the likelihood for the other data point, then probably the first data point is more likely to be seen. So that's what this likelihood function is. You just multiply the probability density functions at the samples you see. Now, a Gaussian model, and the word Gaussian just refers to the fact that we're doing Gaussian distributions, you can think of as just a subset of positive definite matrices of size d by d. Okay.
So, just a quick question. Maybe you're going to talk about this later. But so, can you just give an example? For example, in just one dimension, and you just have the family of Gaussians. Let's say my model consists of only Gaussians with different means and variances. And typically, that's what you want to like. Maybe you want to find mean from the observations you have done. So there, the question you raised was how many samples do we need, right? That was kind of the key question. So
That's
in
right.
one dimension, can you give us an answer like just to clue us in, something like that?
Well, let me think.
Like mean and variance is, I guess, all you need if that is your family.
That's right. So my guess would be that you need about 2 samples.
Okay, so in that case, like error terms and all this, like one doesn't really care about it. Is that correct?
Yeah, I think so.
Okay.
I believe that's correct. Yeah, I mean, okay, I have not worked this out, but if I had to give a quick answer, I think it's maybe 1, maybe 2.
Yeah, yeah, yeah.
Uh,
So I'm guessing if it is perfectly the family of Gaussians, then I think, yeah, I think two will probably suffice.
yeah.
Uh, yeah, as long as I guess two or three. Yeah. Anyway, but the thing is, the errors are not accounted for.
Yeah,
That's
the errors are not quite accounted.
okay. Sounds good. Thank you.
One step at a time, right? Uh, okay,
Absolutely.
so a Gaussian model. Sorry, was there another question?
I had muted myself, and I was when you said one step at a time. I said absolutely, but I had muted myself. But okay, sorry. Go ahead.
A Gaussian model, I just wanted to say, is a subset. So we might not study all Gaussian distributions. You might want to restrict yourself to some subset of Gaussian distributions, which is what we'll keep doing. Okay. So a maximum likelihood estimate is going to be a probability distribution, which will maximize the likelihood. Okay. And this is the distribution that we're after. So let me now tell you some of the models. So what I'm going to do on this particular slide is I'm probably going to tell you I'm going to tell you one big result, and then I'm going to explain all the terms in the result. Okay. So I'm first going to try and define for you a model that's associated to a group. So as I said, we have to bring in invariant theory somewhere. So the way you get to invariant theory is to have a group action somewhere. So you must have a group somewhere. So let me start with a group. This group is going to be a subgroup of GLD, which will act on d-dimensional space by matrix vector multiplication. Now, I'm asking for a bunch of hypotheses, which I don't want you to think too hard about. First is that it's Zariski closed, because I'm an algebraic guy. I want something algebraic. And that it's closed under adjoints. Adjoints is conjugate transpose, and because we know the real numbers just transpose. And it should be closed under scalar multiples. Okay, so we know many such groups. The entire general linear group is already one of them, and you can pick many such classical groups will have this kind of property. Okay, so once you pick such a group, you can define a model, and the way to define the model is to take the G transpose G for each element of the group. So if you took any invertible matrix and you took G transpose G, that's positive definite. And so if you run over the group, you get a bunch of positive definite matrices, and that gives you a subset. So this model itself is not a subvariety or anything, but it is parameterized by something that looks like that is a subvariety. So once you have this Gaussian model, suppose you have m samples, which is just going to be m vectors of d dimensions. Then I want to tell you this theorem, which I will explain bit by bit. And this theorem is kind of very recent, and it's due to 4 people: Carlos Amendola, Kathleen Kohn, Philip Reichenbach, and Anna Seigal. So Carlos Amendola and Anna Seigal are students of Bernd Stumpfels. Kathleen Kohn is a professor at someplace in Finland. I'm sorry, I forget. And Philip Reichenbach is a student of Peter Bergesser. Of course, most of them have graduated now. And So they found this result. And this result explicitly says there's going to be certain statistical notions which they're going to identify with certain invariant theoretic notions. So here's what they do. So in this setup that I just talked about here about this Gaussian group model, they consider not the group G itself, but a slightly modified version of the group, which is to just take all all determinant one matrices in the group. And perhaps this is where you might wonder, this is where something like being closed under scalar multiples plays a real role. Okay, so what are the statistical notions here? The statistical notions are that the likelihood function is bounded for the given samples that you have. An MLE exists, which means that, so what does it really mean that the MLE exists? It means that this likelihood function actually achieves a maximum, right? Because you're trying to maximize it. There's something that achieves a maximum, and it's not just a supremum that's not achieved by any particular distribution. And then the third, perhaps the one that you really want, is that a maximum likelihood estimate exists uniquely. So not just is it that this likelihood function achieves a maximum, but it achieves it in a unique way. And so these are the things in statistics that you would be interested in. And on the other side, in invariant theory, these correspond. Yeah, is there a question? So on the invariant theoretic side, these correspond really to the notions of semi-stable, polystable, and stable, which I will now sort of explain to you slowly. Okay, I mean, these are kind of standard notions in geometric invariant theory. And it's very nice that in this particular setting, which actually is kind of useful in real statistical applications, correspond precisely to these statistical notions that you're interested in.
So why is it called the Gaussian group model?
Okay, so the Gaussian is because we're taking Gaussian distributions.
Okay, so you'll define this later. Or
no, we talked about Gaussian distributions, right? We said Gaussian model is a subset of positive definite matrices.
Right. Okay.
Yeah. So when I took this subset of positive definite matrices, what is the collection of probability distributions? I'm looking at each such positive definite matrix and looking at the corresponding Gaussian.
I see. I get it now. Okay. Thank you.
And the group is just because it's starting from a group. Okay. So maybe one thing that I have to really warn you just a little bit is that the first two statements here are if and only ifs, and the last statement is not really an if and only if, it just exists in one direction. So what you don't have is that if an MLE exists uniquely, it does not mean that you have stability. But I mean, there's a way to fix that and good enough results for what I'm looking for. Okay. So let me look at the likelihood function again, and let me try and analyze it a little bit. So you have this M samples. So I'm doing it in this setting. So you have this M samples, Y1 to Ym, and you pick some probability distribution from your model, which is basically a positive definite matrix psi, and you evaluate the likelihood function. It's just going to be a product of the probability distributions at each of the samples. And if you write it out, you see there is a constant that depends on M, and which I'm going to ignore because it doesn't have anything to do with maximizing psi. And then there's a determinant of psi to the M over 2. Basically, there was a determinant of psi to the 1 over half, which is getting multiplied M times, 1 for each Yi. And then the other terms will just become e to the minus 1 half sum of Yi transpose psi Yi. Okay, that's what the likelihood function looks like. What I'm going to do then is I'm then going to take log just to make it simpler. So if I want to maximize the likelihood function, I might as well maximize the log of it. And if you take the log of it, and I've ignored this constant that only depends on M, then it starts looking kind of nicer, or at least simpler. It just becomes M over 2 log of determinant psi minus 1 half sum of Yi transpose psi Yi. Now I want to just pause there for a little bit and try and do a computation that has that we will see the relevance of as soon as we do it. So we are in a Gaussian group model, which means that your probability distribution can be written as G transpose G for some group element. So then I just want you to think a little bit about what is the norm of G applied to Y what is the norm squared of G applied to Y? And if you sort of write it out, it just becomes a sum of GYI transpose times GYI, and you sort of wiggle it down a little bit, and you end up with this expression, sum of YI transpose psi YI, which is really what exists in the second part of the log likelihood function. Okay, so in some sense, if you were to believe me that the first part is not so relevant, then maximizing the log likelihood function would, there's a minus here, would be the same as minimizing the norm. Okay, and so let me write that down sort of cleanly. So the log likelihood function is just m over 2 log of determinant G transpose G minus 1/2 norm of G times Y squared. And now you might actually, I mean, some of you may have seen things like Kempfness theory. And so norms of vectors along the orbit start playing a role, and you can maybe then start to spot the connection. So you have this log likelihood function. And so here's how I'm going to relate it. So there's a little bit that I'm skipping here, and I will keep that skipped. So I'm going to assume that you can write your group element as a constant times something in something of determinant 1. Okay. Strictly speaking, you can't really do this all the time because you're over the real numbers, but let's ignore that for the moment. You could do this over the complex numbers without issue. Okay, so if I write my group element as some scalar times determinant 1 matrix, then I can try to rewrite this log likelihood function. And you just have to write it out, and you see it becomes md log of lambda minus lambda squared over 2 norm of h times y squared. And somehow there's two dual roles. I mean, so there's two different roles being played here. You're trying to maximize over lambda and an h. And it turns out what you can do is you can first maximize over the h and then pick an appropriate lambda that maximizes the whole value. So I'm going to make this claim, and you can sit down or you can just look at it once. You can look at the paper of Amendola, Kohn, Reichenbach and Seigal once, and you can see it's a basic argument. But maximizing this log likelihood function is the same thing as minimizing the norm along the orbit for this group G sub SL. So I'm going to make the claim now, which is probably the most important claim that connects the two sides, is that this log likelihood function attains a maximum if and only if the norm attains a minimum along the orbit, along the GSL orbit. And here's where invariant theory really comes in, is a celebrated result of Kempf-Ness, which says that the norm along an orbit attains its minimum if and only if the orbit is closed. And okay, so that's how we're walking towards invariant theory little by little. We started with this Gaussian group models. We had this log likelihood function we wanted to maximize, and then we worked on this log likelihood function. We worked on it a little bit, rewrote it a little bit until we realized that to maximize that is the same thing as minimizing the norm. And now we're suddenly feeling more into invariant theory because you're looking at orbits and their norms and so on. Okay. So now let me tell you the notions from invariant theory very quickly. They're kind of not so hard. I mean, if you haven't seen them before, they will seem new to you, but the concept itself is not so difficult to understand in the first instance. So you have some algebraic group that's acting on some vector space, which is another word for a representation. And you pick a vector, and I want to say this vector is called unstable if the origin is in the orbit closure. And I want to say it's semi-stable if the origin is not in the orbit closure. I want to say it's polystable if it's not the zero vector and the orbit is closed. And I want to say it's stable if it's polystable and has a finite stabilizer, modulo whatever kernel exists in the representation. But if you are seeing this for the first time, ignore what's in that bracket. Just think of it as finite stabilized. Okay, so perhaps the only thing that I have to tell you right here is that the closure must be in the Euclidean topology. Although as an algebraist, you would prefer the Zariski topology or something, but you have no choice but to work with the Euclidean topology because that is what statistics demands. Yeah, but it won't be much of a problem. Okay, so now I'm going to tell you the sort of problems that we're interested in, and these are called sample size thresholds. So you pick some Gaussian group model, some subset of positive definite matrices, and you have some M samples. And the question that we're asking is, do we have almost surely boundedness of log likelihood, existence of MLE, and existence of a unique MLE? And so almost surely basically means that this property should hold away from some measure zero set in RD to the M. And as we've seen, now that we have kind of related it to invariant theoretic notions, it's just kind of equivalent of asking whether for the action of this group G sub SL on M copies of RD, whether we have almost sure semi-stability, almost sure polystability, or almost sure stability. Well, stability is not quite the same as existence of a unique MLE, but let's fix that at the end, not now. Okay. But perhaps what really helps with this algebraic perspective is that you can replace this almost sure with the word generic, just because the locus of semi-stable points or polystable points or stable points will be something of an algebraic nature. The right word is constructible. And so the notion of almost sure can just be replaced by the notion of generic. And we will just do that. Okay, so now I'll come to the models that we're really interested in. And these are called tensor normal models. So here I define a vector space, which is a tensor product of k vector spaces, each one's having dimensions d1 to d2, d1, d2, and so on up to dk. Once you have such a tensor space, there is a group acting on it in a kind of a very obvious way. I have the product of general linear groups, and each general linear group is acting on the corresponding tensor factor. Once you have this group, you can even think of it concretely as a subset of GL. So this vector space has dimension product of DI. So if you want to think of it as if you want to think of the group as a subgroup of GL of product of DIs, then you just think of it as Kronecker products of things of size DI by DI. But it's not so useful to really think of it that way. It's much easier to think of it as a product of general linear groups. So associated to this particular group is a tensor normal model. The Gaussian group model that's associated to this particular group action is called a tensor normal model. And it's nice that I will also tell you what this group G sub SL in this case, it just happens to be a product of special linear groups. Okay, so now if you forget about all the things that I've said, you can sort of just rephrase what I'm looking for in a very algebraic manner. So I give you M and the dimensions D1 to DK of the tensor space, and M is going to be the number of samples. Then you look for the action of GSL on this tensor space taken M copies. And I'm asking, do we have generic semi-stability, polystability, or stability? So I want an answer that takes in the numbers M, D1 to DK and gives you a yes or no for generic semi-stability, polystability, and stability. Okay. So here's an example of a question like this, which I feel could be really useful in many places. For example, I could ask you, if you looked at a generic tensor, a generic three-way tensor in Rn tensor, Rn tensor, Rn, and you looked at the orbit of SLN cross SLN cross SLN, is that orbit closed? Maybe I pause for a second. Does anybody know whether the orbit of a generic tensor in Rn tensor, Rn tensor, Rn is closed? Or would anybody like to take a guess?
I mean, the way the question is phrased, let me go with no, and we'll see how I fare.
All right, we will find the answer. So there is no hurry here. Okay, so anyway, I mean, irrespective, maybe what I really want to emphasize here is that this is the kind of question that you could pretty much ask anybody who's doing some sort of algebra, and and both things exist. Like they will be able to think about it in a meaningful way, and for all you know, they might have some good application for something like this. And perhaps that's why I'm trying to drive home this kind of simplistic version of the main result. All right, so let me do a few examples. So I'm going to pick my tensor product to have dimensions. So I will call the dimensions of the tensor product the local dimensions. So the local dimensions are going to be 2, 3, 5, and 176, and I'm going to take 2 samples. Now, I'm going to just do the example for you to sort of give you a feel for what kind of arguments we're using. So I'm trying to consider the action of SL2 cross SL3 cross SL5 cross SL176 on two copies of this tensor space with local dimensions 2, 3, 5, and 176. You can think of this tensor space as like a four-dimensional matrix with sides 2, 3, 5, and 6, and just a big, four-dimensional block with entries. And two copies of that. So for the action of this group on this, I want to try and understand whether generically something is, whether generically a point in this vector space is semi-stable, polystable, or stable. So you might wonder why I picked these particular numbers. There's of course nothing all that special about these particular numbers, but maybe one feature that you really want to see is that this number 176 is a lot larger than any of the other numbers involved. And this is the feature that I want to sort of exploit. So I know I'm trying to look at this larger group, but let's just look at a smaller group. Let's just look at SL176. And if you look at this vector space as just an SL176 representation, then it just becomes 60 copies of R176, where SL176 acts on R176 by like matrix vector multiplication, and it's 60 copies of that. So if I restrict myself to a smaller subgroup, it sort of becomes a simpler representation, something that I can think about. Much easier. Okay, so let's hold that for a moment, and let me then now tell you a fact. So one fact is this. So if you took the action of SLW on W, where W is any vector space, it doesn't matter what, then I want to say that all non-zero points form a single orbit. This should be very elementary. All I'm claiming is you can get from any vector to any other vector by a transformation whose determinant is 1. This is a very simple exercise that you could give an undergrad who's starting linear algebra. It only takes a minute to figure out. So, but what does this tell us? This very simple fact will basically tell you that if all non-zero points form a single orbit, then you take any point, its orbit closure contains the origin, right? So all that means is that every point is unstable. Now, what's the relevance with the issue of uphand, with the issue that I just, with the situation that I just told you about, is that the same kind of argument will tell you that every point is unstable if you look at the action of SLW on m copies of W, as long as the number of copies is smaller than the dimension of W itself. Okay, it's sort of the same argument. If you can prove this easy fact, then you can prove the next statement, and then you can prove this fact. It won't be hard at all. But I will skip it. It's also very well known. It's a very standard result in invariant theory. One of the first things you might learn. And so basically, that same argument will tell you that if you already view this as just the smaller group SL176, then you have 60 copies of R176, which means every point is unstable. So let's think about what that means. That just means that every point, its orbit closure contains the 0. So if the orbit closure for the smaller group SL176 contains 0, then the orbit closure for the larger group G sub SL will also contain 0 for every point. So this means that every point in this vector space is unstable with respect to G sub SL. And maybe I just point out the only feature that I really used is that this number 60 was smaller than 176, which I could have done in complete generality. All that meant is that m times the product of all the numbers involved other than the largest one, dk, or maybe just one of them, dk, the product of all the other numbers should be smaller than this dk. And if you have that, then generically you'll be unstable. Not just generically, every point is unstable. So this actually takes care of a large chunk of cases, is what I'm trying to say. Okay. Now let me give you some more examples, which I don't really intend to tell you why currently this is. I don't tell you why this is the particular way it holds, but just to sort of try and drive home the point that it's not quite. I mean, the answer might not be quite as simple as you might expect. So I'm just going to stick to one sample, and I'm going to change the dimension vectors. And this dimension vectors, even in the dimension vectors, I'm going to fix the first two local dimensions to be 2 and 3, and I'm going to vary the third one to be 1, 2, 3, 4, 5, 6, 7. And you can see the behavior sort of moves from unstable to polystable, but not stable, to polystable to polystable. And then it again falls to unstable, and it goes back to polystable, and then falls to unstable. Maybe some of you can spot a pattern here. It's not all that easy a pattern to spot, but in any case, so all I really want to say is that the answer is not like there's a nice curve or something that separates one region from the other. the answers is kind of all over the place, and you need to find a way to get hold of it. Okay, so just sort of keep this in mind, and maybe try and think about what exactly is it. For example, like what exactly is it that's making 235 unstable, but 234 is okay and 236 is okay? Right? This is the kind of thing that can really bother you a little bit as to why these things aren't working the way they are. All right. So given these examples, let me tell you what my strategy is really going to be to give the answer to this. So the property of being generically semi-stable, polystable, or stable is invariant under this notion that I'm going to define for you called Castling transforms. And so what you're going to end up doing is I will tell you this notion of Castling transform that relates two different setups to each other. So and then we're just going to look at the minimal elements in each Castling equivalence class and deal with those. So it's not, so what does this Castling transform do? It really says if you were looking for m copies of a particular thing, of a particular dimension vector, and you want to know whether it's generically semi-stable or polystable or stable, you can also look at m copies of a different dimension vector and study that instead. And the answer for both will be the same. And so once you do that, you can sort of just look at the minimal elements in the equivalence class and just study it for those.
So minimal in what sense?
Well, once I tell you what the Castling transforms are, the minimalness will be evident. Yeah. Yeah, I mean, in fact, you could put whatever measure you feel like and study the minimal in that sense, right? We'll pick one that's easiest for us, and it almost doesn't matter. It's kind of it'll show itself.
Okay.
So let me first tell you what Castling transforms are, and I will do this in slightly greater generality than we really use, just to try and, because Castling transforms I think are also of independent interest. I think these are also things that people could use in various situations. So I want to try and tell you a little bit about Castling transforms. So suppose you had a group that acts on W being a vector space, and the dimension of this vector space was n. Then you have an action of H cross GLK on W tensor RK, where H is acting on W and GLK is acting on R to the K. You also have an action of H cross GL n minus K on W dual tensor R to the n minus K. Well, if H acts on W, then H acts on W dual in kind of a standard way, and GL n minus K acts on R to the n minus K. Of course, you want K to be smaller than n, otherwise it doesn't make sense to write GL n minus K. So I have these two actions, and I'm going to relate them in some funny way, which is what I want to call a Castling transform. So the first thing is, if you pick something in W tensor R to the K, anyway, so this two tensor, so it's just two tensor factors, right? You can think of them as matrices of dimension W by K. And I'm going to just do that. So if you took any tensor in W tensor RK, you could write it as sum of Wi tensor EI, and the sum goes from I equal to 1 to K. I apologize, there's a typo here. This K, so this E1 to EK is a basis for R to the K. So you can always write it like this, and then you can write a matrix that basically looks like whose rows are W1 to WK. Now, what's the size of this matrix? The size of this matrix is going to be K by dimension of W. And some of you may have seen this before, and some of you may not, but a full rank matrix of size K by dimension W can be thought of as a point in the Grassmannian of K planes in W dimensional space. What is the Grassmannian of K planes in W dimensional space? It's basically an algebraic variety that parameterizes all K dimensional subspaces of W. Now, what is a K dimensional subspace of W given by? It's given by a spanning set. You can give K linearly independent vectors, and that defines for you a K dimensional subspace of W. And this matrix is basically doing that for you, where it gives you W1 to WK. It's K vectors. If they are linearly independent, then you get then you can think of it as a point in the Grassmannian. So when I put this arrow here, there should really be a dotted arrow, because it's not going to work for every tensor, because it'll only work when these Wi's are linearly independent, but that sort of happens in a generic sense. So we'll leave that. Now you can also do this for the other setup, where I look at W dual tensor R to the n minus K. And so points in W dual tensor R to the n minus K also you can think of as points in the Grassmannian of n minus K planes in W dual. And what is the real connection? The real connection here is that the Grassmannian of K planes in W is the same as the Grassmannian of n minus K planes in W dual. Okay. So if I gave you a k-dimensional subspace of W, you can think of it as an n minus k-dimensional subspace of W dual by looking at orthogonal complements. And that's what that thing is. And that's sort of equivariant with respect to GLK and so on. Sorry, GLW in particular H. Okay, so once we have this kind of idea that you can relate both these sides, what you really have is sort of a series of correspondences. So the series of correspondences, I look at GLK orbits in W tensor RK. Of course, not all the orbits, just the ones where the points have maximum rank when looked at as a matrix. Those will correspond to points in the Grassmannian of k-planes in W dimensional space. Those correspond to points in the Grassmannian of n minus k-planes in W dual, which correspond then to GL n minus k orbits in W dual tensor R to the n minus k of a certain rank, of full rank. Let's just think of it as full rank. So once you have these correspondences, you get a correspondence that basically says, look at H cross GLK orbits in W tensor R to the k, and those are the same as H cross GL n minus k orbits on W dual tensor R to the n minus k. I have to be a bit careful here. I don't really want the orbits on the entire vector space. I want to restrict myself to some Zariski open set on both sides. And then this is an actual correspondence. But that sort of is sufficient for us. And I'm not going to give you the details. There's slight things that you have to change, but you can replace GLK with SLK and you still get the same sort of statement. But perhaps what's most important about this kind of a correspondence is that it preserves the stabilizer. So when you have a group acting on a vector space and you take a point, then the stabilizer is the set of all elements of the group that keep the point, that send the point back to itself. And so if you look at the stabilizer of a point on the left-hand side with respect to H cross SLK, there's an orbit there. So there's a stabilizer there for some point. And then you look at it on the right-hand side, you get the same stabilizer. But what do I mean by same? I just mean they're isomorphic. They cannot be the same in any sense because they're subgroups of different groups, but they're isomorphic. And that's all we really care about here. All right. So now I'm going to apply this Castling transforms to tensors and see what exactly this is doing for us. So you started off with some setup where you had M samples and you had local dimensions D1 to Dk. And here the group that you're interested in is a product of special linear groups. And the vector space you're interested in is you take the tensor product and you take M copies of it. And that's what you want to understand. And you want to understand these notions of stability in a generic sense for this particular action. Now, suppose that, so first of all, I might not have said this explicitly, but I'm really thinking of D1 to Dk as being ordered. So Dk will be larger than Dk minus 1 and so on. Okay. So suppose the largest number Dk is smaller than the product of everything else. Then I'm going to try and set this up in a Castling transform. Then I'm going to try and fit this into a format where you can apply this Castling transform. So I'm going to take this group H to be a product of the special linear groups, but only up to k minus 1. I'm going to take W to be this tensor product, forgetting D sub k and taking M copies. And now I want you to sort of notice that the situation that we're looking up here, where I'm looking at a product of SLDIs all the way up to k acting on this tensor space, is the same thing as H cross SLDK, which is what the group is that you want, acting on W tensor R to the dk. That's the vector space that you really want. And so Castling transform will tell you it's sufficient to study the other side of it, which is H cross SL capital N minus dk acting on W tensor R to the N minus dk. And if it really is equivalent, then the latter could really make your life simpler. For example, if capital N minus dk is 1 or something, then you sort of, this R to the N minus dk, if it's just 1, then it doesn't really matter too much. Then you just look at H acting on W. That sort of, I mean, of course, it could also make it harder if N minus dk is larger than dk and so on. But in any case, the answers for both these setups are going to be the same. But let's look at what this H cross SL N minus dk really is. So if you look at what H cross SL N minus dk acting on W tensor R to the N minus dk is, it's again a tensor action. It's again really just a tensor action where you still have M copies and the local dimensions are D1 to the dk minus 1 and capital N minus dk. So I've really related two tensor actions, and I'm going to tell you now a little bit more specifically about how it relates to notions of generic stability. Okay. one thing that I will say here, but I won't really get into, is I've ignored duals somewhere, and you have to be careful when you ignore duals. But if you are, then you know what you're doing, then it's okay. All right. So what are the properties of Gaussian transforms? Why am I so much after these Gaussian transforms that I'm really after them? So a result that I can date back to at least Sato and Kimura is that Gaussian transforms preserve generic semi-stability. So if you look at both sides of the Gaussian transforms, then one of them you have generic semi-stability if and only if you have it on the other side. And then Elashvili, which is even earlier, showed that they preserve stabilizers. And why is this important? Why is it so important that the stabilizers are preserved? Is because I'm going to tell you a theorem of Popov. Of course, Popov proved the result where the underlying field is the complex numbers, but then that's okay. It still gives you it still gives you an idea of why we want this. Is that, so Popov said, if you want generic polystability, then you look at this stabilizer in general position. It should be reductive. What is a stabilizer in general position? This, of course, only exists when the group is complex numbers. But it really says, you look at the stabilizer for most points, it's all going to be isomorphic to this one special subgroup. And that special subgroup is called the stabilizer in general position. And if that is reductive, then you have generic polystability. So why is it important in terms of Gaussian transforms? Is Gaussian transform preserves stabilizers, which means that if the stabilizer in general position on both sides is the same up to isomorphism. So one side is reductive if and only if the other is reductive, which means generic polystability on one side if and only if the other side. And then generic stability is only asking for the stabilizer to be finite, which is okay, because if it's finite on one side, then it's finite on the other, if it's isomorphic. Okay, so that's what Gaussian transforms do. They preserve these notions, so which means I just have to study one side, and that gives me the answer for the other side of Gaussian transforms. Once you have that, what do you then do? Then, so let me give you an example of how exactly you might work this out. So initially, let's say you look at m equal to 1 and d equal to 2, 3, 4. This is already a non-trivial case. You have a 2 by 3 by 4 tensors. You look at tensors of size 2 by 3 by 4, and you look at the action of SL2 cross SL3 cross SL4, and you want to know if generically the orbits are closed or not. And it's a bit of a subtle question. You might not immediately be able to do it because tensors are hard to work with. 3 tensors are already pretty hard to work with, so you might not be able to do it quite as easily as matrices. But what does Gaussian transform do? So the first thing we do is we look at the largest number 4, and capital N was the product of all the other numbers, which is just 1 times 2 times 3, which is 6. That number was greater than this largest number 4, which means I'm allowed to do a Gaussian transform. And that Gaussian transform will replace this number 4 by the difference of n minus dk, which here in this case is just 2. So to understand 2 by 3 by 4 tensors is the same thing as understanding 2 by 3 by 2 tensors when you have one copy. Once you do that, I'm just going to reorder them, because if you reorder the tensor factors, it doesn't really change anything. Once I do 2, 2, 3, I'm going to again try and do a Gaussian transform. And when I do this Gaussian transform, I have 3, and the product of everything else is 1 times 2 times 2 is 4. So 4 minus 3 is 1. So I replace 3 with 1. And now, if you think about it, if you have a tensor factor which just looks like r to the 1, you just completely ignore it. It doesn't do anything to you. Which means really, I have to look at one copy of 2 by 2 matrices. Now, again, this is a very simple question now, and anybody with some amount of undergraduate algebra should be able to think about it, and it won't be so hard to solve. You could even give this as an exercise. Is what happens if you look at the action of SL2 cross SL2 acting on 2 by 2 matrices, one acting on the left and one acting on the right? And the answer is generically the orbits will be closed, but the stabilizer will not be finite. So it's generic polystability, but not stability. In fact, this was one of the examples that I put out in that page where I took m equal to 1, and then I changed the local dimensions from 2, 3, and then from 1 to 7. So this is the kind of argument that would actually answer one of those setups. Actually, this is the kind of argument that would answer all of those, almost all of those. Okay, so what really happened here is somewhat magical. You started with 2 by 3 by 4 tensors, which are not quite that easy to handle. Tensors get far more complicated than people would naively imagine. And we somehow did this Gaussian transform a couple of times, and then you ended up in a situation that was very simple. So if you're looking for SL2 cross SL2 acting on 2 by 2 matrices, then really the orbits are parameterized by the determinant. That's not so hard to understand. And then you can just find all the answers. All the answers sort of work themselves out. So I just want to make one sort of warning here, which is kind of annoying from the statistics perspective. But so the fact that 2, 3, 4 transform to 2, 2 when you had one sample does not mean that 2, 3, 4 will transform to 2, 2 when you had two samples. And the reason is because this number capital N that I write, which is a product of everything else, if you had one sample, it's 6. If you had two samples, it would be 12. And so why is this slightly annoying is that from the statistics perspective, you might have hoped that if you, for one set of dimension vectors, and then you did a Gaussian transform, and the number of samples you required on one side is the same as the number of samples you required on the other, it doesn't really work that way. What it does say though is if you fix the number of samples and the dimension vector, then you Gaussian transform, and the answer is yes to both or no to both. Okay, so that's a bit of an annoying thing if you're trying to write down a threshold function. Okay, so now that we know that we can just look at any particular thing in the Gaussian equivalence class because the answer to all of them is the same. Let's try and understand what are the minimal ones. So really, what do I want to do? I want to do such a transformation if n minus dk is smaller than dk. That's all. I'm just trying to minimize something reasonable. You could try to minimize product of di. You could try to minimize sum of di. You could try to minimize anything that's sort of monotone in the di's, and then the minimality turns out to be one of three things. So the first thing is that this number dk is just much larger than n, in which case you can't do a Gaussian transform because n minus dk would be negative. And then there's also the case, which I really should have just said greater equal, but I'm going to split it into the case where this number dk is equal to the product of n, in which case, again, you can't do the Gaussian transform, but it's a somewhat nice situation. And then the third situation is when I won't do this Gaussian transform if n minus dk was larger than dk, which in other words just becomes dk to be smaller than half times n. Okay, so I actually want to kind of clear up some of these cases very quickly. So the first example where dk was much larger than the product of everything else was that first example where I took these dimensions to be 2, 3, 5 on this large number 176. That same argument will take care of the first case and it'll tell you it's generically unstable. For the second case, you have to work at it a little bit, and then you can compute this stabilizer in generic position. It turns out to be reductive, so it's generically polystable. But then you can also see that it's not a finite thing, so it will not be generically stable. And then for the third case is probably the slightly more complicated one. And so I will tell you very briefly where this is coming from. So you have this notion of an index in representation theory. So if you have a group, well, I really want this group to be semi-simple and connected, which I didn't write. I sort of forgot to write. Its index is given by, you take a generic element in the Lie algebra and you compute a ratio of traces of squares. Now this thing has a meaning of its own, and I won't really get into what this index does. It's a ratio of certain bilinear forms that have to be invariant and so on. And it plays some sort of role in other parts of representation theory. But we sort of borrow this notion. And then there's a result of Andrei Winberg Elashvili and further results of Elashvili, which tell you the following. It says, suppose you have a product of simple groups, in which case we do. In our case, it's just a product of special linear groups, which are all simple. And you have a representation. Then you compute the index of the representation for each of these simple groups. And if that index is greater than or equal to 1, then you have generic polystability. And Elashvili went further and said, look, I can actually classify for you all the cases where you have generic stability. And there are only a few exceptional cases where you have generic polystability, but not stability. And what is, yeah, maybe I skipped this note. Index is not preserved by Gaussian transforms, not so important. But what's really important is in this case, this where dk is less than or equal to half times n. If you really compute these indices, they really just fall into this theorem and you know the answers. So that sort of clears up the answer in some sense, because now given any number, now that somebody gives you a number of samples and a particular set, particular local dimensions, you can tell whether you have generic semi-stability or not. which is the same thing as saying you can tell whether you should expect the likelihood function to be bounded, or we should expect an MLE, or to expect an MLE uniquely. Well, okay, I said something about uniqueness of MLE not being the same as stability. So let me be kind of brief about that. So you really only have to worry about the cases where you have generic polystability but not generic stability, because in these cases you could still have a unique MLE. But then a unique MLE means a compact stabilizer. And we will show that in all the minimal cases where you have generic polystability but not generic stability, you have some slightly large enough set. I'm just going to show a Euclidean open set where the stabilizer is not compact. And this means that you don't have unique MLE almost surely for this particular case. And then you can transfer this property through Gaussian transforms, so you are happy. If you couldn't transfer the property through Gaussian transforms, you would be stuck again with that little bit left over. Okay, so I'm going to skip that a little bit. So basically, the final the conclusion is that generic stability is the same thing as an existence of a unique MLE for tensor normal models, and this is not this is after the result and not something that you get before the classification. All right, so what am I going to do now? Now I'm going to just yeah, of course, it's not true for general Gaussian models. Now I'm going to tell you what the main result. So I'm just going to present to you the final result. So what you really want is an answer that doesn't really ask you to do Gaussian transforms to find the minimal element and so on. And so you can define these quantities. There's a quantity called R, quantity called G max, and a quantity called delta. And based on those quantities, if you just compute those quantities, it will fall in one of these three setup. And once you have that, you can decide. This is just a recasting of everything that I told you before. Okay. Anyway, so that's basically what I have now. That's the final result that I want to tell you about. You can take a look at it. I will put out the paper in maybe a couple of weeks once we finish final nitpicking. But where is the subject headed? So the subject is headed in some exciting directions. I'm just going to put them all out and tell you one by one. So so you have statistics and you have group actions, and you can go both ways. You can try and find good group actions that you really understand and see what statistics is on the other side. Or you can find interesting statistical models and you see whether the invariant theory that corresponds to it is within reach or not. And some of this I'm working on with Cole Franks. And perhaps another direction is really kind of strengthen these results that Amendola, Kohn, Reichenbach, and Seigal have done. Is basically you have all these notions in invariant theory and representation theory, just because people have been studying these things for a long time. And you wonder, I mean, we have some real non-trivial results, as you would in any subject that's mature enough. And then you sort of wonder how many of these results actually mean something in the statistical setting. And this, of course, requires you to talk to statisticians and see what exactly they want and the kind of questions they care about, and see how much of invariant theory can really play, we would really like invariant theory to influence statistics in a meaningful way. And we are working towards that. So I'm going to stop there.
Thanks, Vishnu, for a great talk. So if anyone has any questions, they can unmute themselves and ask Vishnu. Yeah. Okay. So let me. I had a couple of questions. One of them was you made a remark about it being some of related work being used in finding craters on the moon. So
yes,
could you tell some generic stuff about that?
Well, I mean, it's not related to what I talked about today.
Okay.
That was a remark based on a recent paper of harm reduction. I don't quite know the details, so let me start.
Okay. All right. No
I don't quite know the details, but
yeah.
I can talk you to the paper.
Yeah. So, or do you have any concrete examples of groups? Like for example, here essentially you have this Gaussian group model. Like you have a bunch of concentration matrices which kind of come from groups, and that's the family you care about. So, is there like a natural problem like in real world which like kind of associates with a certain group? Like, is there like
that's a very good question, and I'm a bit disappointed that I forgot to say this at the right moment. But tensor normal models already are very useful, and the reason is sort of something that people are getting more and more used to nowadays, more familiar with, is that when you collect data these days, it occurs in a high tensor format.
Okay.
We really do collect data in high tensor format these days. Okay, you call it whatever you want. You call it data analysis. You call it whatever things you want. So sometimes, I mean, no matter what kind of data you're collecting, there's going to be several pieces of information that you're going to collect, and it's just naturally going to end up as a tensor. And then it is quite as natural to expect a distribution to also be Gaussian. This is not, I mean, this is something that people have been assuming for a long time, with good success. So tensor normal models themselves are already kind of very useful. They're used all over the place. I didn't pick tensor normal models just because I could answer the question in invariant theory. I picked it because people were interested in tensor normal models.
Okay. Yeah. So these are like I can't claim to understand everything, but I think these are very important keywords to remember. Yeah. Okay. Are there any other questions?
Yeah, I have a sort of a generic kind of question. So what is the, can you hear me?
Yes?
Huh. So I mean, I guess this is a theorem, but what is the idea behind this thing that some orbit being away from zero has something to do with likelihood function at a existence of MLE? Yeah. So what is the crucial?
Yeah. So I guess at this moment, I'm not sure I'm the one who understands it most cleanly. But the way I look at it currently is that I took this likelihood function and I kind of messed with it. I sort of saw that it really depends on the norm, on minimizing the norm. So
Yeah.
currently, I can, yeah, I'm afraid I can't give you too much intuition as to why exactly it works. But currently, I view it as sort of you look at this function, you stare at it, you modify it, you sort of rewrite it a couple of times until you write it down into something that looks like an invariant theoretic.
Okay. Okay. So I guess that paper may have it, that 4-author paper.
Yes, you could certainly look at that paper, but I guess in many senses, it definitely. So as far as I understand, how did somebody come across this? Is because they looked at certain formulas and they looked the same.
Okay. Okay.
I think that's how the connection was made. But of course, I mean that paper may have some more intuition, but I couldn't catch it. Yeah.
Can you hear me?
Yes.
Are the models other than Gaussian models studied, or people think it's not necessary to go beyond Gaussian models?
It definitely is necessary to go beyond Gaussian models. For example, Cole-Franks has some results on Tyler's M estimator and so on, where he goes way beyond, beyond Gaussian models. I'm a little hesitant to say exactly what he's done, but he says something about exponential families, which I don't quite know what it means. But it certainly is worth going beyond Gaussian distributions. It's something we should do, but we're taking baby steps. I think we've just gotten into this connection, and we have to grow. Yeah.
Yeah, I mean, I guess one of my interests in like hearing about invariant theory, I guess this is an offhand remark, this is not really a question, was there are many such notions that can like also be useful in studying finite von Neumann algebras, because they are kind of you can think of as continuous matrices. That's how we think of like 2-1 factors and so on. And I had been working on some, like rank, for example, is a kind of invariant that you get from GL action, right? Like from both sides. So,
Right.
so yeah, that was the kind of my interest in this topic. But yeah, so that's my remark. Yeah.
Thank you.
Okay, thanks a lot. So I guess if there are no more questions, we will just adjourn the meeting.
Yeah.
Okay.
Can we clap?
Yep. Clap for a great talk. Yeah. All right. Yeah, have a good trip to Melbourne. Yeah, see you sometime.
Yeah, thank you very much. It was good to do this.
See you.
Thank you. Bye. Take care.
Bye bye.
Bye.